I'm an experimenter. I do high energy physics. I concentrate on hadron colliders where we take protons or antiprotons or lead nuclei, smash them together, and we look at what happens when they have this collision. I've worked at pretty much all of these machines. Recently, as pointed out, I was the physics coordinator of ATLAS. This is one of the Large Hadron Collider machines. I was responsible for the scientific output of that. I'm very much what you would call a domain scientist. I'm not a CS person. So what do? We collide particles together. We measure the energies and the trajectories of the particles that are produced. And you can see that's a beam's eye view. You're seeing the particles produced radially. We then compare these results with simulation, and we do this at multiple levels. So anyway, this is a very complicated process, and we're absolutely as dependent on the simulation side of the chain as we are for the real data side of the chain. Right? And that's the real problem. And we use right now about 1 billion CPU hours a year on this. So I'm going to talk about 2.5 things. I'm going to talk about what problem we're trying to solve, where our limits are, where we are on the way to a solution, and kind of a little bit about what the future might look like. I was asked to focus on performance and portability. I think that was to serve as a negative example to others. So this is what the experiment looks like. It's about 5 stories tall, 75 meters long. Those 2 people that look like ants are actual people. This is what it looks like in real life. All right, this is the actual detector. Those 2 small people there, the thing they're standing in front of, those are the small wheels. So that gives you kind of a scale of the whole thing. So science outputs, we discovered the Higgs boson in 2012, and that led to the 2013 Nobel Prize for Peter Higgs and Francois Englert. We have 418 papers. When I wrote this slide, we're now up to 421. We've done both searches for new phenomena and precision measurements of existing phenomena, and there's 1 or 2 papers per week that are coming out. This is a picture of one of the Higgs boson candidates. These 2 particles are called muons, there and there, scooting up through the detector. They're highly penetrating, and so they're basically sitting outside of the multi-thousand-ton structure. We have electrons there and there. They absorbed in the detector, and then there's a bunch of other particles there. So we make many events that look like this and try to infer the physics from them. OK, so what are we going to do? Discovery of the Higgs boson was nice, but what have you guys done for us lately? You know, the Nobel Prize was in 2013, for heaven's sakes. Why haven't you come up with another one? It's rather puzzling that the Higgs weighs what it does. It's too light to be heavy, and it's too heavy to be light. And this suggests that there may be some new physics lurking just around the corner. We also don't know if we found the Higgs boson or if we found a Higgs boson. We have to look at that. We don't know what dark matter is, other than it makes up about 1/4 of the universe. But it sure would be swell if we could make some in the laboratory and study it. So to answer these questions, we've got a program to collect about 100 times as much data at close to the design energy of the machine. We've run at half the energy so far. So how does this work? As I said, we compare 2 data chains. We start on the simulation side. We have what's called event generation. We simulate the physics of interest. We produce lists of particles and their momenta, and then we do this again and again and again. The next step is simulation in the green. We simulate the interaction of these particles with the detector. We have to understand when we produce an electron, how does it behave in the detector? What sort of signals do we expect to get from it? There's about 100 million channels, electronics channels from ATLAS. How do these particles fill, and how do they populate these channels? And finally, there's reconstruction, where we take this and we infer what must have been present based on the detector response. On the real data chain, we only have reconstruction. Right? Then the analysis compares the 2. Do we see what we expect, or do we see, for example, an excess of events of a particular kind? This slide doesn't fit anywhere else, so I stuck it in. The key element here is what we call the event. In principle, it's a single proton-proton interaction. In practice, because we have so many events going on at the same time, it's that interaction that we're interested in, plus 20 or so that happened in the same, more or less the same space in the same time. When we record the event, we get the one we want, plus these other 20, and we call this pileup. We write 600 of these, each of them about 2 megabytes every second. There are 10 to the 7th running seconds in a year, which is about 6 billion events per year. So you can work this out. We're talking about roughly 10 petabytes every year coming off of this. And simulation, we need a comparable number, say 2 billion events per simulation campaign. We run 1 or 2 of them per year. So it's very natural to assign one event per rank in absolutely everything that we do. And then when it's done with that event, we give it another one. And this single event becomes our quantum of computing. People have used words like embarrassingly parallel to describe that. As you can see from this shirt, I'm not embarrassed by much of anything. Right? Pleasantly parallel is what people have used. I've actually had good luck in proposals by saying it's pre-parallelized. So, how do we reach our science goals? I said we use about 1 billion CPU hours per year on the grid. This doesn't include cycles spent calibrating the data the first time. It's basically defining the problem after that point. And by the grid, I mean the worldwide LHC computing grid. It's about 140,000 Xeon class cores. They're distributed in about 100 farms worldwide of varying sizes. Typically, each one has 2 gig of memory, and jobs that you send are typically single core running 12 to 24 hours. This is sort of a picture of the relative fraction of time spent simulating, generating, and reconstructing. So let me say it in the right order. Generating, simulating, and reconstructing. You can see the bulk of this is simulation. That is, how does the experiment, how does the particles react with the detector in the experiment? So, what problem are we trying to solve? We have 16 million lines of code. I wish I had never written that number, because when you say 16 million, what people think you mean is a lot. But I actually mean 16 million lines of code. 45% or so is the experiment's code. The remainder is common code that is used across multiple experiments. Every one of these 16 million lines of code was written under the assumption that computing is expensive and memory is cheap. Every last one. Almost all of the 16 million expects to be run single-threaded. So this is sort of the environment I'm faced with. But the needs of the experiment are growing exponentially. Every 3 years, the data volume triples, and we have 4 triplings planned for the future. The grid is not going to be growing exponentially. So we've got a mismatch that we're coming just in computational capacity. But the complexity of these events are also growing. There are jobs that simply can't run on the grid. They run out of CPU. We discovered the first one about 3 years ago. They were highly filtered events. So we ran a bunch of events that only give us one that looks like this. And it turned out the mean number of events that you would get from the job was about 1, which meant that 1 over E of the jobs failed because it produced 0 events. But the grid was smart. It saw there was no output, and it resubmitted them, and resubmitted them, and resubmitted them. And eventually, a human being had to take a look at this and say, wait, this is a problem. Right? So this is sort of showing that we're beginning to outgrow the grid, not just in its size, but in its capability. So this is why we're interested in high-performance computing, despite, and I'm being polite here, the non-optimal nature of our code. So I'm going to talk about the first piece of code is something called Alpgen. There's a link there. This is a generator. It simulates the physics process of interest, and at the end of the day, you get a list of the particles and their momenta. It's written in Fortran 77, as God intended. There's an optional F90 part in it. It actually speeds things up rather a lot. It's about 250,000 lines of code. It runs in 3 phases, what's called the warm-up, where it pre-calculates certain phase space integrals, the actual event generation, and then something called the unweighting, which I'll talk about in 2 slides. And then there's a 4th piece that we add after it that's not Alpgen, which lets us interface this with the rest of the Atlas code downstream. This makes up about 5% of Atlas grid computing, and we hoped when we put in our ALCC proposal that we would do something like 40% of this. 2% is a number that's big enough to be interesting if you succeed, but small enough not to completely torpedo the experiment if you fail. So we wanted to kind of get that middle ground. So how did we get it to run on Mira? The first thing we did is we started with a single Alpgen process and we got it to compile. Now this was not completely trivial, but that was the first step. The second first step, oh, I've got this wrong already, is to run multiple copies of the same task. This works beautifully, but I now have 4 identical copies. So I haven't actually helped anything here. So the next piece we needed to add was a dispatcher. Basically, this is very little bit of MPI code, 10, 20 lines, to do some coordination of the work. Basically, what we had to do is give each rank its own random number seed, so we would be generating different events as opposed to the same events. Doing this and only this will run in a minimum Mira partition. All right, 512 nodes by 32 ranks per node, but it's seriously I/O limited, and I'll talk to you about that later. Also, the random number seeds, we're using them here in the minimum partition 16,000 times faster than we are on the grid, because every time we start a job, we need 16,000 seeds. So you really have to coordinate with the experiment so you're not generating the same events multiple times at multiple different places. That would be bad. So a year ago, we could run in the minimum Mira partition, and only in that partition. There's our job there. I was really happy to see this. It really was. I mean, this is, for you guys, 512 is nothing, but for us, this was just absolutely incredible. The event generation was a whopping 1/15 of a grid node, and they give you a little sheet when you get an ALCC at Mira saying suggest about 1 in 10. So we figured 1 in 15 versus 1 in 10. We're doing about where we should. OK, the trick now is to get to the full machine. Major changes to the code were absolutely impossible. It's not our code, and more importantly, and you heard some of this, it's been validated by the experiment. The experiment has looked at this and said, OK, the output of this code is fine. If we start monkeying around with the kernel, we break that, and it takes many people many months to revalidate it. So we really wanted to leave our fingerprints off this as much as we could. We were able to reduce the memory footprint. There are various models of the proton that you put into these calculations. And the way Alpgen works is it loads all the models into memory, and then you pick one. We decided it made more sense to do that in the other order. You pick one, and then you load it into memory. And by doing it that way, that got us down to under 180 megabytes per rank, which let us go to C64 mode, and that gave us almost a factor of 2 improvement. So instead of using 32 processes per node, we were able to get to 64. We moved the output from the file system to a RAM disk so we could collect, and then collected it all later. Right? Now, that sped things up because the output's going to RAM and not a physical disk. But it also means there's a certain tension for the best use of memory. If I have a byte of memory that's free, do I use this to run more processes to get us from 32 to 64? Or is it better to use this for more RAM disk and allow for longer jobs? Yes, sir?
So how long do these simulations take on Mira? I know you mentioned 12 to 24 hours on Geant 5, right?
Right. So
how long does a single simulation take on Mira?
So we're getting right. Could you hold that thought for just a second? Because I'll get to where we are at the end. It turned out we ran into another bottleneck: standard in, standard out, and standard error. If you have 2 million threads that are running, it doesn't matter that none of them are writing anything. The mere fact that they could be writing something gives you a little tiny bit of overhead, and when you multiply it by 2 million, that's serious. And I've got that picture of this traffic jam here. It doesn't matter if those trucks are empty or not. Right? What matters is the number of trucks, not their content. So if you work out the bandwidth, you say there's no reason that the machine can possibly have to worry about these, but it's the sheer number of trucks. So our target in fixing all of this was always improved scalability. The word performance never appears on this slide. But in the process, it sped up the code by more than a factor of 20. So today, one Mira node is 1.5 times faster than a grid node. So running the equivalent of a 12-hour job will take 12 divided by 1, what's it, 8 hours. Right? Now, in fact, we don't run the jobs the same way because we want to go broad and thin. Right? So instead of one long, skinny job, which is 12 hours long and does as many events as you can do, we typically run jobs in 16K partitions for 30 minutes because we get the best throughput that way. So this is where we are today. I like looking at this even more than I like looking at the other one. Right? This is running the whole machine. Now, normally, for throughput reasons, we limit ourselves to 1/3 of the machine. If you ask for 1/3 of the machine, you get it in about 2 or 3 days. If you ask for the full machine, you get it once every 2 weeks when they shut the machine down for maintenance, either right before or right after. So to get the most out, the most real science out of this, 1/3 is the sweet spot. We did this, and the experiment said, great, here's our work for the next 2 years. Can you do that for us? So we took that on. While this job was running, Mira is the equivalent of 5 or 6 grids. So it's kind of like a supernova. For that brief moment, this is the brightest star in the galaxy. This is, for those of you who run on Mira, you get these every week. The green are the small partitions, the blue are the medium, the red are the capability, and you can see how we've progressed as we've improved in the I/O from only being able to run in the smallest partitions to regularly running in the largest partitions. And this slope here, which is what we got after that request, is 600 million hours a year. So if we had 600 million hours worth of work a year, we could do that. So we got a ALCC 2014 award, which is now over. It was for 50 million hours, of which we spent 62. And I would, again, like to publicly thank ALCF for making that possible. The equivalent on the grid is 70 million. The reason it's not 1.5 is it took us a while to get to 1.5, so the integral is smaller. Have been offloaded from the grid and run on Mira. This took about 2 FTEs worth of effort. That's me, Taylor Childers, and Tom Urim, who will meet tomorrow. In fact, if you just said it's Taylor and Tom Urim, that's about right to 99%, but that's who did it. If we were a country, we would be the 7th largest provider of cycles to Atlas, and if you turn the cameras off, I will say that makes us the same size as Spain. However, I'm not allowed to say that. Now, this is only event generation, only the red. But once you've moved them off the grid, you can use the recovered cycles to do anything that you want. So one of the things that people said before we started this is you'll never get all 1,500 transforms, the 1,500 sorts of jobs we run, to run on these supercomputers. And my point is you don't have to. Because once you've moved one over, you can use what you've recovered for any one of those 1,500 jobs. A job is a job is a job. OK, so what is this unweighting I promised to talk about? When an event generator makes an event, it assigns the event a probability of occurring. So when you unweight the event, you generate a random number. If it's less than the weight, you keep it. If it's greater, you toss the event and never look at it again. Alpgen does this as a separate step. See, I really need to practice these more. This is efficient because you can rescale to the highest weight that you produce. Typically, the event with the highest weight is about 1%. So instead of throwing everything away there, you scale it up so that the highest weight is at 100%, and you get 100 times as many events. Right? The whole purpose of this is to make the generator output, which has a list of events and weights, look like the data, which has those weights already reflected in it. And this will be important as I go to our next target, Sherpa. Sherpa, and there's a link there, is an event generator very similar to Alpgen. It attempts to capture more of the physics, as opposed to Alpgen, which attempts to get the right answer. That was funny. It's 10, 12% of Atlas grid usage, so it's about twice what we did for Alpgen. It's written in C++. It's about 700,000 lines of code, and it knows about MPI. We thought this was great. This is not a blessing, it's a curse. Because it knows about MPI, but it was intended to speed up desktops. So it's thinking about MPI as how you would deal with 8 ranks. And it makes certain design decisions which make perfect sense for 8 ranks. There are some n-squared algorithms based in this. Right? N-squared works beautifully with 8 ranks. With a million, not so much. It's code that writes code. So when you run it the first time, it writes out object files that contain the code for the actual calculation. So you then run it in a separate phase, a second phase, which reads them in and does the actual calculation. So the 3 stages here, it writes the code for the calculation. This is single threaded. Then it does the phase space integrals that Alpgen did. Then it generates the events. There is no 4th stage afterburner that's required. There's a little bit of format fix-ups, but that's fairly straightforward. So let me talk about these phase space integrals. They take between 1 and 2 weeks per process on a single core. This is too long for the grid. We had a site in Dresden which is doing all of this, but the experiment needs a few thousand processes. We have 421 papers, so you can imagine if you need a few processes per paper that you're checking out, this easily scales to the thousands. MPI helps, but not as much as we'd like. Scalability initially topped out at about 60. And with some tricks, we've got this thing up to 200 to 300 before we start petering out. Our record is 768, so we're able to run with 768 parallel cores and still scale. Now, this fits nicely as a 3-node Edison job. Normally, I would be embarrassed to be submitting 3-node jobs, but again, I'm not easily embarrassed. And we've submitted hundreds of these because we needed to get it to do the science. If we could fix this problem, we could calculate processes that are too complicated to be calculated today anywhere. So we're highly motivated to be working on this. Now, the way this works with MPI is you have some volume that you're trying to calculate, which that funny shape is supposed to represent. And then you have each rank work on one of these slices that I had, and then you add them all up later. The equal spacing means that some ranks finish sooner than others. So the way you try and improve the scalability is you try to get unequal spacing. You try to arrange things so that each rank has roughly the same amount of calculation to do, and therefore they finish at roughly the same time. But there's a limit to this, because if you knew the areas exactly, you wouldn't have to do the integral. So you can only guess so well. So where are we today? Our record is 16K cores, 8 per node, which is 131,000 ranks. The scaling is awful. A 16K job has no better throughput than a 12K job, which is 100K ranks. So I've been saying we scale to about 100,000 now. Even this is a little bit of a cheat, because the 12K job actually runs 12 1K subjobs, each in its own directory. Right? And this is one of the ways we've been getting around I/O problems. So what are the limitations? Sherpa absolutely loves its I/O. If there's a chance to read something from disk, by goodness, it's going to do that. One example, the subprocessors are typically stored as 1,000 plus or minus a factor of 2 object files. Now, the authors, we've been working with them, and they provided an option to consolidate this to 6, and it's a factor of 50% to factor of 2 speed up, just because it's not always hammering these files. There are thousands of file opens in the course of a job. It's got a parameter file. Every time it needs a parameter, it opens the file, reads everything into the point of the parameter it wants, stops, and closes the file. That's, well, again, on a desktop, well, what's the difference? Running the jobs in its 12 subdirectories, each with its own complete copy of everything, helps, but eventually even this peters out. And Sherpa uses 1 gig plus epsilon per rank, just enough to preclude running in C16 mode. And one of the things we've been thinking about is, can we cobble together a pseudo C12, where you ask for 16 ranks, only 12 of them are actually doing the calculation, and the rest is a RAM disk. Or maybe we could start squeezing it into a smaller footprint like we did with Alpgen. So again, this is the same sort of question we had before. Given a certain amount of memory, what's the best way to use it? Is it by throwing more processes at the problem, or is it by staging the output and input into a RAM disk? The design has problems with a very large number of ranks. It generates a fixed number of events per rank. Now, Alpgen does the same thing, but for Alpgen, it takes, to within about 1% or 2, the same amount of time to generate one event versus another event. Sherpa, there's a factor, it could be a factor of 100 between the fastest and the slowest. Typically, it's more like 10. So what you can have is this happening. So you've got one guy which has got this really, really long thing, and everything is waiting on it. I can't release this partition until this last guy finishes, and most of this time is then wasted. Don't like that much. Sherpa also unweights on the fly rather than as a separate step. So because it does that, if you've got a low probability thing, it keeps generating events, tossing them, generating, tossing, generating, tossing. So all of these make Sherpa susceptible to these stragglers. The initialization takes about an hour. This makes debugging difficult, because you have to wait an hour before you can check anything. And I've asked the question, what can it possibly be doing? An hour is 1 trillion calculations. This is more than put man on the moon. What could possibly take 1 trillion calculations? And I've asked the authors, and all I get is important initialization. So it's doing important initialization for 1 trillion calculations. Now, I have no doubt that we're going to sort all of this out. I could have set the same sort of list of complaints about Alpgen a year ago, but this is real work. This is not something which just magically happens. People have to go and hammer things a little at a time. All right, let me talk a little bit about simulation and where we are. This is the green part of the diagram. When I drew this, it was about 70% of the usage. It's falling to 60%, and that's partially my fault, because by making the red go faster, people are now asking for more red. And it's squeezing out the green. It uses a C++ toolkit called Geant4. It's about 1 million lines of code. This is the only program HEP uses for this, because they made it modular. If you want to try a different interaction between matter and your detector, you know there's this module gets unplugged, that one gets plugged in, and you go, but you keep the framework the same. As user code, this is really very, very nice. It identifies the position and the amount of energy deposited in each part of the detector, and energy is really all that matters. If you have enough energy, you're either measuring energy, in which case you need to know the energy, or you've got a digital device, in which case you need to know if the energy is above a threshold or not. I've called it an HEP code, but it actually goes well beyond that. The three on the outside I knew about before I put this talk together. They use it to do radiation effects on satellites, a lot in medical physics, things like dose calculations or development of new sensors. But I think the first one's kind of cool. It processes, they use it to study electron avalanches in thunderstorms. Because, again, this is electrons interacting with matter just on a much lower scale. So here's how it works. And you see this jagged step here. Basically, it takes a little step, and then when it takes a step, one of three things can happen. It can either just deposit some energy along its track by ionization and take the next step and so on, and the code is designed to do that most of the time, or it could create a new particle, like in the blue, and then adds to this list of particles, or finally the particle is stopped or exits the detector. So you've got a number 1, a number 2, and a number 3 there. So Geant starts with the particles that are produced in the collision, and typically there's a few hundred of them, right? And it continues until the particle list is entry. It makes some, it kills some, and eventually it all runs out. And this takes typically, say, 10 minutes per event for a typical ATLAS event. We understand the average scaling very well. It scales basically by the amount of energy that you put into the detector. So if I double the energy, it takes twice as long. So this is a picture of a real electromagnetic shower. What happens in here is you've got a particle coming in this case a gamma ray, hits a piece of material and produces an electron-positron pair. Each of these hits some material and emits a photon, which then produces another electron-positron pair, and so on and so on and so on. And this continues until all the electrons stop and all the positrons are annihilated. So you've got typically thousands of these secondaries. This is a schematic view. This is a Geant simulation where you can see all of the individual tracks are put through. So what's on the right is what we actually end up doing. That's for an electron or a photon. Particles called hadrons, like the proton, the neutron, and its cousins, have showers which are a little bit wider. But the same basic thing happens. Particles are produced or destroyed. And these images are actually simulations of cosmic rays interacting in air. So the reason it blows out so far is that the density is low. Electromagnetic showers all look the same. Doesn't matter which one they are. And hadronic showers are like snowflakes. Everyone is unique. So we have a model for the ATLAS detector. There's a picture of it there. It's been used for about 5 billion simulated events so far. It has 400,000 volumes. Each of these represent a total of 100 million readout channels. And to keep the volume count low, it takes advantage of symmetries of the detector. If I rotate certain detectors by a factor of 8, I get the same thing, other ones by different numbers. The simulation runs inside our homebrew framework, and it takes about 2 gigabytes each, single-threaded. So you can quickly see the problem of moving this. The authors of Geant now have a multi-threaded version, 410. It takes a detector geometry and what's called the physics list. The physics list determines how particles interact with matter, and it makes them read-only and shared. Because if I'm simulating ATLAS events, I don't need to have detector geometries for other experiments there, just ATLAS, and all the threads can share it. This lets us go from C8 mode on Mira to 64 threads. So there's a factor of 6, should be 8. The scaling isn't perfect. And in fact, you can overcommit to 80 threads, and that moves 6 to 6.1. And you can see the scaling here. It's more or less linear, and once you cross the number of physical execution units, yes, it's incrementally better. But this moves us from something that's difficult to run to something reasonable. The scaling has also been looked at in present generation PHYs. You see the same basic behavior here. It's linear up to about 60, and then it kind of only grows slowly. There's several development directions that are going on that are relevant to us. 30% or so of the time is spent in 2% of the code. Perfect. Perfect. But Geant still has 2,000 classes. So 2% of the code is still a lot that has to be ported. People are talking about using GPUs. This is a substantial job. There's 2,000 classes after all. Most of the time is not spent in a single routine. You've got 100 things each taking a percent. And people are even talking about a complete refactoring of the code. So what I said before, we could and we intend to double this 65 million hours or so that we're using by running Sherpa. If we can scale the Sherpa integration phase, this could increase by an order of magnitude. That's good, but it's also going to increase the demand. And ultimately, we want to scale the number of simulated events to match the number of real events. And without HPCs, it's not going to happen. Virtually all the simulation could be done on HPCs. The kernel runs today. The software framework would have to be ported. It runs in Edison today, but basically by accident. So we're going to have to figure out how to do that. And unlike event generation, this is data intensive. So we're talking about many, many petabytes. And it's not really clear what we could do with analysis, but I do want to spend 2 minutes talking about how we might improve things. So if you read one of our papers, you'll say, suppose I've got a theory that has 2 different parameters, say particles that aren't there. We take a grid of points in this space, and we look at every point and see, is it allowed or is it excluded by the data? And based on the outcome of these tests, we interpolate an exclusion curve in the blue. Now, these points are run on the grid today, so they're all run in different places and at different times, so there's no opportunity for coordination. You send them out to the grid, 90% of them come back, and you decide, well, do I need to submit that last 10% or not? But what you could do instead is use an iterative grid. You could start with a coarse grid, and depending on where you are relative to the exclusion, to run a finer and finer grid. The program can coordinate, and now it can converge on a better answer even faster. There are actually fewer points on this plot than there were on the one before that. So the past slide shows how you could get better limits at reduced computational cost, but what if you decide you want to increase the computational cost? Well, we have models with more than 2 parameters, and we look at this now in 2D slices because all the other parameters are constant, and they say, well, to do anything else, we need a supercomputer. So could we set 3D limits? And one argument is 2D slices don't easily separate a picture that looks like this, a moon, with that, because that's not a moon. You might want to know the difference. So to conclude, HEP is a non-traditional user of HPCs. Our codes have co-evolved with high-throughput farms, and now the ultimate in farms, the LHC computing grid. But even so, starting with the low-hanging fruit, the event generators, we're now providing computing equivalent to a medium-sized country. Soon to be Canada. Moving on to other event generators and simulation digitization will allow us to grow, and HPC deployment is also growing. And in fact, it's growing faster than we will. Right? So our fractional use of these systems, even if we grow, is going to be about what it is today. It's just going to be a larger part of the experiments computing ecosystem. And adapting these codes is challenging, but it's possible. And I would argue it's necessary. If we want to reach our science goals, there's really no alternative to this. And we're starting to see the benefits now. So that's all I have. Any questions? Sir?
Yes, I'm wondering, have you compared running Alpgen on Blues or Fusion to see how long it takes?
An MPI version of that? We haven't, but we have run it on Tukey.
Okay.
And
we're doing a similar thing in internal combustion engines, and we see that on Blue Geant Q takes about 10 to 12 times the runtime, and we are in a situation where we're doing these embarrassingly parallel sort of simulations as well. And also the initialization was taking us over 2 hours.
Good. Tell me what you're doing.
So we did NPI all go all V, and it was a lot faster, which it was not taking so much time on Fusion or Blues. So I'm just wondering maybe if that's something that's...
So one thing I know, where does this factor of 1.5 come from? Basically, most of it comes from the factor of 4 in the number of execution units. So each core in Blue Geant has 4 execution units, whereas Pentium is 1. So I get that factor of 4. Then there's this division by whatever the clock speed is, so that gets you to maybe 2 or so, and the code is slightly less efficient. So that's where it all comes from.